All right, it seems we are ready enough, so let me start. I will introduce our first speaker, Moritz Futscher. Is the CEO and co-founder of BTRY, which is a Swiss startup developing sustainable and fast-charging solid-state batteries. Moritz holds a PhD in physics from the University of Amsterdam and led pioneering battery research at EMPA here in Zurich. Today, we'll present this talk called Thin Film Solid-State Batteries from Fundamental Insight to Scalable Solutions. Moritz, thanks a lot for joining Fluxim. The floor is yours, and we are really happy to see what you are saying.
Perfect. Thank you very much for the introduction, and also for giving me the possibility to present a battery here in the Fluxim Research Seminar. To start off, batteries really shaped the world which we are living in today. They allowed communication and also the wide use of, for example, renewable energy. But even though they have enabled so many applications, there are still limits to what they can do. And specifically, if you look at the comparison between energy and rate. What does it mean? Energy is how much can your battery store per, for example, volume or per weight, and rate means how quickly can you actually use this energy for an application. How much power can you generate with these batteries? And historically, we have here two different applications. One is a lithium-ion battery. They are known for having very high energy, and that's why they also allowed, for example, the electrification of cars, but they usually have a limited rate performance. So even the best batteries today usually take an hour to fully recharge from 0 to 100%. On the other hand, we have capacitors. Capacitors have carry little energy, so they're not good for example, any portable electronics, but they have very high rate, meaning high power applications. But today there's not really a technology which can provide both in one simple device, and this is really something what we can enable at battery. And very briefly, what are we developing, and what is the cells, the batteries which we're promoting? These are really thin film solid state batteries, and we'll go a bit more in detail what this is later. But they're unique in a way that they're very thin. They are just 0.1 millimeter thick, and which makes them thinner than the packaging of a traditional battery alone. And this really enables the integration into applications like, for example, card and labels. We can charge them very quickly, also discharge them in just 1 minute, which really also allows the high power application, and then often eliminating the need for capacitors in some devices. They're fully solid state, meaning that there's no liquids inside, that they cannot burn, and there's no risk for explosions, and they're stable across a wider temperature range because they're solid state. But let's take a step back, and what is actually different compared to a conventional lithium-ion battery. On the left side, you see a conventional lithium-ion battery. They're usually made out of different materials, usually composite materials. So you have a mixture of for example, in the cathode material, which actually is the one which is storing the energy. But then you also have additives to increase the conductivity, both electronic and ionic, to really enable the transfer of lithium ions through these cells. And then you have an anode and a cathode. And then usually you have liquid electrolytes in these cells. Liquid electrolytes are very good in transporting ions, but they have the risk of that they can burn, and they can lead to explosions, and they limited the temperature operation. We really work on thin film solid state batteries. So first of all, we don't have any liquids inside, and second of all, the layers are much thinner. And we use pure materials. So we don't have any composites anymore, but really pure materials. And these materials, the full cells in the order of tens of micrometer thick, whereas a conventional battery is in the order of hundreds of micrometer thick. So these are really some key differences in the cells itself, which then lead to the unique features. But these thin film batteries are nothing new. They're actually already around since quite a while. In the late 60s, the first primary thin film batteries were reported, and then the first secondary in the early 80s. And secondary means that you can recharge the cells. But then really the field really started kicking off in the early 90s, where with the development of a new solid-state electrolyte, this is the material separating the anode and the cathode from each other, by Nancy Dudney in the Oak Ridge National Laboratory. And this is really one of the still widely used solid electrolytes today, which also allowed for, which then shortly after that, really the commercialization started of thin film batteries. There have been many companies developing thin film batteries. Thin Energy, for example, is one of the companies which later on also got acquired by Apple. And then in 2014, another great result was published by Oak Ridge National Laboratory. They showed that these thin film batteries can actually cycle for 10,000 cycles, which is 10 times longer than classical lithium-ion batteries today. And what is unique about these, they are fabricated using vacuum processes. So processes which are also used in different industries, such in the OLED fabrication, but also PV fabrication and semiconductors. They usually are very good if you have very precise layers and thin layers you have to deposit, which then allow for high quality, precise control of the layer thickness. They can be fully automated. And this is an industry which is already established for different applications. So there is actually equipment off the shelf which can be used for the production of these systems. But I told you now that this is already quite an old field. So I would like to now start what actually have we contributed to this field. Now this is from the research side. So what we have done at the thin film solar cells, the laboratory for thin films and solar cells at AMPA. And I would especially like to focus on two key research works which we did. On the anode side, where we actually reduced the amount of lithium by going for an anode-free design, and I will explain in a bit what this actually means. And on the cathode sides, by reducing the amount of cobalt in the cathodes by transitioning away from lithium cobalt oxide cathodes, which is the most frequently used cathode in the thin film batteries, but also in classical bulk batteries. So to start off with the cathode work, this is really work which was done by Abi Abdesselam, who is also one of the co-founders of BTRY. And he showed that he could fabricate a new material with these vacuum coating processes in a thin film format. And then he also showed the difference between if you use it in organic liquid electrolyte, like classical lithium-ion batteries used today, or in a solid-state electrolyte. So if you go to a liquid electrolyte, you typically cycle somewhere between 3 and 4.3 volts. Here you see more or less stable cycling performance. But as soon as you go to higher voltage, in this case 4.7, or lower voltage, in this case 1.5, you see strong degradation happening and side effects happening. This is because the liquid electrolyte degrades at these high and low voltages. It's not stable at these voltages anymore. If we now transition to a solid-state electrolyte, we see that we can stably cycle at even an extended voltage range. In this case, even getting more capacity out per weight if we go for 1.5 to 4.3 volts. And we can do this in a stable manner. And he also showed that this material in a solid state configuration, we were able to cycle this for more than 1,000 cycles, where in this case the cycle life is 904 cycles. This is usually defined in batteries when the capacity reaches 80% of the initial capacity. So this was basically one of the starting points of one of the cathode materials which we actually developed in the research group, really replacing this LCO, which is frequently used. On another side, on the anode side, and this is really where I focused on during my research time, we were able to fabricate cells without an anode. So what does this mean? In a classical battery, as I've shown before, you usually have a cathode, the electrolyte or the separator, and then the anode. Now, the best performing anode in terms of weight, energy per weight, is lithium metal. Lithium metal is very difficult to handle and also has usually the tendencies to grow in dendrites. Dendrite is basically a spike which goes through your cells, and this can short circuit your cell. And then, of course, the cell is not working anymore. So one interesting way is here to, first of all, replace, remove the lithium metal in the cell design itself, which avoids using lithium metal and fabricating lithium metal thin films. The other one is having an anode interface where this lithium metal grows and disappears homogeneously without this dendrite formation, without the risk of short circuits. And here you see part of the cell. So the copper in this case is the current collector. The lipon is the solid-state electrolyte, which was developed by Oak Ridge National Lab. And then on top of that, we have lithium metal. And in the end, what we want to have here we would like to have the anode. And in this case, we developed interlayers and tested different interlayers to have homogeneous growth. And we could find one interlayer, in this case carbon, where indeed the lithium metal was able to grow very homogeneous here in a thick layer. And you even see that the shape of the current collector here is still visible up here, which really shows you that this lithium metal grows in a very homogeneous manner. And then this would be basically then in a charged state of the battery. And then if we discharge or remove the lithium, we can fully remove it again. And this really allowed us to make an anode-free battery or a lithium reservoir-free battery, where we don't have any anode during the fabrication, but then the anode is only formed once you charge the battery the first time. And then we brought this together, both Abi and I, and we actually were able to fabricate such an anode-free solid-state battery with a nickel-rich cathode, which Abi developed, and we could show that this performs relatively well. And this was really one of the starting points of the startup itself, where we saw that the performance in the lab works well, and we also saw that there's an interest in industry for such a technology, and this was then the starting point where we said, okay, let's think about starting a company. And then from starting a company, there were many different other challenges which were involved. One of it, for example, was scaling, because in research we usually work on very small areas. You see here one which is 3 millimeters squared. This is good enough for research and for understanding fundamentals of materials, but not enough for product. So what we went to do is we scaled this area, and here we worked with a partner, which is Asahi Glass Company, which is one of the largest glass producers globally, and also produces these vacuum coating machines. And here you can see our journey. Initially at EMPA, we pushed up to roughly 100 square centimeters, which is the maximum which we can do at EMPA. And then immediately we had to switch to larger systems, in this case rented systems, where we are now at a roll-to-roll system in Germany, where and you see the machine here, where we can deposit on very large areas. At the same time, we needed to decrease the speed. So here you see what we were used to in research times. It took about 50 hours to fabricate one of these cells. And over the time, both optimization of processes, changing the processes to go to more industrial-sized, scalable processes, but also the systems which we're using, we were able to decrease this to below 5 hours today, and with a promise to give even much lower than that in the future, while simultaneously increasing the yield of the production. So these are really two key aspects which we did as a startup, increasing the area and decreasing the deposition time to have a higher output. But now you wonder what does this mean on performance? And we also looked up at the data, historical data on the performance of these cells. And before incorporation, you see the dots here where we have been in the research time. And from time-wise, you can think is that this is basically, there's always a year between each of these dots. And then we started incorporating the company and really scaling the area, but also the speed. And what happened here is the capacity went down to almost zero. but the speed went up. So basically increasing changing the systems, the speeds and the processes and the systems. But then we also learned to handle these new recipes to fabricate cells with a high capacity, with a high speed. And here you see the performance was a bit all over the place. And this was really our first interaction with customers, and then building cells according to the customer's requests, where we see a lot of fluctuations in the performances. And then we at some point also understood and standardized our cell design. And you see that now we're really increasing the capacity. We're already above 0.2 milliamp hours per square centimeters. And this is now already enough for many IoT applications. And these are cells which we already ship out to customers for first validation and also integration into devices. And now, how does such a cell perform? And in the beginning, I told you that our technology is really in between a capacitor and a battery. We want to share you some of our data of one of our cells. And here you see a cell which has a capacity of about 0.4 milliampere hours. But this cell with this little capacity is still able to drag very high currents, in this case above 20 milliamp in current, which means these are C rates of 50. C rate is how often can you charge and discharge a battery in 1 hour. So 50 is close to 1 minute. A C rate of 60 would be exactly 1 minute, and a C rate of 1 would be 1 hour. And you see that this cell with a very low capacity can still deliver very high currents, which really shows you the unique properties of this technology. If you now would want to drag this currents of above 20 milliamps with something like a coin cell, you would probably need capacities in the orders of 20 to 100 milliamp, because they can really only deliver the energy in a very slow manner. And this is really where batteries usually fail. And that's why you often in IoT devices combine a battery with a capacitor. And this technology really can replace it and still electrochemically be a battery, store the energy for a very long time, but if needed, deliver very high current peaks. Then I also would like to show you some demonstrators of how these cells work. So on the left, you see one of our first demonstrators. Here we simply placed an LED on top of our cell, and you see that the LED lights, and you see that this small foil here can store energy. And here one of these foils is in the order of tens of micrometers thick. Then we also changed the system, so we can also use, for example, USB charging to power one of our cells, but also solar cell charging. And here, for example, the USB charging, we charged the cell with the USB, and then now we disconnected it, and then we use the switch here to power an LED. Or with a solar cell, same principle, now just not with USB, but with a solar cell, where we can charge the battery and then power an application. And these are really the first demonstrators which go into the direction of IoT devices, which are often combining something like a solar cell with a battery for really delivering power at a remote location. And this is really what our battery can do, but not only the energy for powering an application, but also the power peaks which are needed then to transmit the signals. For example, if an IoT device measures a certain unit like the temperature, it needs to transmit it. And this is what we can do with our technology. Finally, very briefly, would like to mention the team. So Abi and I, we co-founded this company together, also with Jaroslav Romaniuk, where the research was originated in his group originally. Right now, we are a team of 12 people, really ready to industrialize our first product and scaling our product. And we are also supported by different advisors, which I mentioned down here. And again, I would like to thank you for giving me the possibility to present what we are doing at BTRY. And I very much look forward to your questions. Thank you.
Thanks a lot, Moritz. I suggest we are moving forward with the second speaker, and we are leaving the questions. We are collecting questions and leaving the question to the end. And now I would like to introduce Stefano. Stefano Sem is one of our colleagues at Fluxim. Is an R&D engineer which is specialized in the development of advanced instrumentation for energy and displays. Stefano holds a PhD in physics from the University of Augsburg, and at Fluxim is developing our new tools for the characterization of especially thin film batteries. And today I would like to introduce Stefano, introduce his work, and listen what he's up to. Stefano, the floor is yours.
Yes. Thank you, Daniele, for the introduction. Let me share. Yeah, so today I will give you an introduction of Fluxim new battery testing prototype, and in general about the effort that Fluxim is making into this field of batteries. Yeah, let me start with the pointer. Yeah, so we host this seminar, so probably you know who we are. That we are Fluxim, so a company located in Winterthur, and we make simulation software and hardware instruments for the characterization of OLEDs and solar cells, so light emitting devices and light absorbing devices. And what we want to do now in batteries is we want to transfer our knowledge in these two fields for the battery industries. Some of our products were already used for the characterization of batteries. For example, PIOS was used together with a temperature-dependent sample holder in this study shown here. So I will not go in details about the study, but simply was used the impedance module of PIOS was used for the characterization of batteries. Specifically, was used to estimate the ion conductivity, its temperature activation, and the density versus mobility. And additionally, what was used is this equivalent circuit fitting from the software of PIOS, so that the impedance of the battery can be fitted with several circuit elements, and yeah, the characterization can be properly done. So that's why we decided to join a meeting. Actually, the Moritz, the previous speaker, was the PI from EMPA of this project, and these were a few institutions working on the project. So there was IREC from Barcelona, Jülich from Germany, Innova, Eichstron, and also Fluxim. And from our side at Fluxim, we joined the project with the goal of developing new software and also measurement hardware products for the testing of batteries. And so here is already the prototype, so where we are now with the development of the hardware instrument. So you see that the prototype is divided in two. So we have the measuring electronics and the temperature chamber on the left. So it's a combination between electrical characterization together with a thermal characterization. So now I will go quickly through the features of the instrument. So the instrument has 8 channels. It has galvanostatic or potentiostatic control, so the current or voltage can be controlled. There are 4 current ranges: 300 milliamps, 1 milliamp, 10 microamp, and 100 nanoamps, and 1 voltage range, but pretty large, so from -10 to +10 volts. Impedance can also be measured sequentially through the 8 channels. Potential impedance, so EIS, but also galvano impedance, GEIS. And the frequency range goes from 0.1 microhertz, so pretty low, up to 200 kilohertz. This is true for EIS, and for GIS it goes from 0.1 microhertz up to only 100 kilohertz, so yeah, not the 200 of EIS. Temperature control. So you see here, as I said, on the left there is the temperature chamber. It's pretty large because it's designed to be used with the pouch cells, but it can also be used for coin cells. The temperature range goes from 10 to 90 degrees, and there is a seamless control via the main software itself. So of course everything is integrated to make the life of the user easier. There is also integrated data analysis. So what I mentioned before that we can do in PIOS, so this impedance fitting already from inside the software. Of course, this will be transferred also in this software here, so that the user can easily fit the data that were just measured with equivalent circuit analysis initially, but probably later also with some artificial intelligence tool to have a proper fitting of the data. And then also another feature is that there is a web-based interface. This means that the instrument can be easily accessed from any devices connected on the same net from everywhere without the need of installing anything. So like if you want to check the status from your laptop or from the phone or from the tablet, it will be easily done without installing any software. And also multiple users can use the instrument at the same time simultaneously, and also the other way around. So the same user can connect to 8 instruments if he has 8 instruments simply by opening another tab on the browser. So where we are now, so here are the quick definition of the product stages that we defined at Fluxim. So we have the demonstrator phase, which is the first stage where we prove that the requirements of what we want to do can actually be met. Then we have the pilot product phase where we extensively test the instrument internally, and then we have the prototyping phase. At this point, we can already give the instrument out to early adopters, and then we have production when we really start selling the products. So here we were at the end of the A3 SSP project, which was February this year. And now we are here towards the end of the pilot product phase where we are testing the instrument internally. So if from the audience there is anyone interested to be one of the early adopters of the next phase, please just let us know, and then we can discuss. Here is a screenshot of the recipe creator. So here is on the platform itself, on the software where the user creates the experiment. So here ideally one can add multiple steps. And here is an example of a cycling step. So the cycling step is done by the charge card, the discharge card. In the charge, of course, the user can set the current that he wants, the voltage limit. If he wants an additional constant voltage step with a certain duration, here can also be added as a limit instead of the duration, can be added a certain current limit. So until the current reaches a certain threshold, then this voltage step is finished. One can add also an impedance, EIS or GIS step at this point. Can also say if the impedance needs to be done every cycle or every whatever number of cycles. And then there is a resting phase, which can also be added with a certain duration. Then the discharge phase would be simply identical to the charge phase, but refer to the discharge. And of course, here you cannot see, but the user can, in the end of the rest of this step, also add the number of cycles that are required. And then, as I said, one can then define multiple steps. For example, here there is a cycling, then you change temperature, cycling again, change temperature again. So this is the idea of leaving the user the flexibility of building the entire recipe. Yeah, and here, if the user goes to the data viewer tab, then it can plot the results. And here are the results simply exported. Here is the cycling of this battery, which is actually running at the moment. So there were 4 to 5 cycles at the point when I generated the images. Green is, of course, the charge, red is the discharge. Here there is an impedance measurement at the end of every charge or discharge step. So we have 4 impedance after the discharge and 4 impedance measurement after the charge. Here is the real part of the impedance versus frequency. Here is a call plot. And this was done on a commercial rechargeable coin cell with a charge current of 3 milliamps. voltage level of 2.3 volts down and 3 volt up. And then there was also a constant voltage of 1 hour at the end of the charging phase. And then impedance, as I said, was done from at the end of every charge and discharge cycle, and from 1 Hertz up to 200 kilohertz with an AC amplitude of 20 millivolt. Yeah, here it's just the impedance enlarged. Yeah, and then I would switch on the software side. So as I said, we produce also commercial software simulation. For example, here I would talk about Setfos and how it was and still used and improved in the field of batteries. At the end of the Anode-free SSB project, we reached the status where we were able to perform simulations and transient simulations. Here, for example, is a distribution of the ionic species through the stack of a battery. Here, these results were shown in the poster at SSI in July last year, and also at the Swiss Battery Days conference last year in August. Here is another result that we reached. So from the optical module of Setfos, we were able to fit ellipsometry data. Basically, ellipsometry was done in operando during charge and discharge. And then we fitted this data and this ellipsometry data with Setfos, so we were able to define the two species here, which will be the charge or discharge electrode. And you see that at some point, depending on the thickness, you have a different percentage of the charge or the discharge. But we didn't stop there, so we continually developed Setfos for batteries also after the end of the project. In this case, we made a simulation. This is a GITT, so it's current pulses. And we see here a comparison between Setfos and Dandelion, which is a well-established simulation software used for batteries. And we see that the results are pretty much identical for the entire curve. We also made simulations combining the transient, but also AC. So here is a transient, which is a charging curve of a battery. So you see the voltage is increasing when you charge with a constant current of 0.2 amps. And here we can already do simulations of the impedance data at certain point. So here, after 18, 36, 54, 72, and 90 minutes of charging, we have an impedance simulation. Yeah, and these are very, very fresh results of Setfos. Yeah, so I'm already at the end of my presentation. Thank you for the attention. If you have any question. Yeah.
Thanks a lot, Stefano. It's great to see also in this presentation of the philosophy of Fluxim, right? Always combining simulations with the development of the new instruments with the idea of combining both simulations and characterizations. And now we are ready to start with all the questions that we have here for Moritz and for Stefano as well. I can start with the first one, Moritz. They are asking you if there are applications of your newly developed technology that cannot be matched with conventional batteries. So where do you have a unique take?
Yes, thanks for the questions. There are a few different aspects. And one, for example, is the temperature stability. Today's batteries usually have liquid inside, and they often cannot go above 80 degrees C, because after that, it becomes a risk for fire. There are applications where you need high temperatures. This can be, for example, in monitoring of industrial processes, for example, steam leaks, or in medicine, where you would like to clean your devices using an autoclave. These are all hot temperature processes where today batteries cannot be used. Another one is the form factor. For example, the thinness of our cell. Today's batteries, the thinnest batteries which you find today are in the order of 0.5 millimeter thick. We can produce them much thinner than that. And that's why we can fit the batteries into application where previously was not easily to integrate them. You can think of something like an RFID label. These are labels which are placed almost everywhere in all kind of products to track the product. But there you cannot fit a battery inside easily. And then here we offer a solution that to integrate batteries into these applications, which then allow to actively transmit signals.
Oh, great. There's another question. Could you give a short comment on the discharge rate of your batteries? They are interested in knowing a little bit more, especially on the milliampere per hour per gram, milliampere per hour per centimeter cube.
Mm-hmm. So first of the rates, the one cell I showed you was a rate of 50 C. So this is really we can go above 10 C, and we've demonstrated up to 60 C in the rate performance. And this is really unique for the thin film batteries, because usually classical cells usually are in the order of a few Cs maybe, but not higher than that. In terms of energy density, we are a solid state lithium-ion battery. So we are similar in terms of energy density than what other solid state battery companies promise. It's higher than a classical lithium-ion battery. Cannot go much more in detail on that.
There is also another one interested in the size of your batteries and the dimension for the different layers to reach such a high C rates.
So for the high C rates, it's critical that you have these thin layers, and that's why vacuum coating techniques and thin film systems are ideal for that. Because in the end, if you can imagine, if you have a classical cell, you have hundreds of micrometers you have to travel through, and of course this comes with a resistance, so you cannot quickly travel through 100 micrometers, and we are in the order of a few micrometers to tens of micrometers for all of our layers, which then allow for the high C rate.
Mm-hmm. Another
and
one
then for the dimensions. Sorry for that. For the dimensions, so they are very thin, in the orders of tens of micrometers sometimes, but you can stack them on top of each other if you need higher capacity, for example. And then from that area, we usually work with a few square centimeters to tens of square centimeters. This really depends on the application.
Another one for you, they're asking you if you can share which technique do you use to coat the reduced cobalt cathode metal oxide.
Mm-hmm. Well, I can tell you what was used in the scientific paper, because this is all public. I cannot tell you what we are using now. In the paper, this was sputtering, so RF sputtering in that case, and we stick to vacuum coating techniques also for the company, but we changed the processes to be more in line with what industry uses for scaled up processes.
Let me ask a question to Stefano. Stefano, you were showing this new instrument from Fluxim. Surely I'm working for Fluxim as well. I would like to just you to comment on which the unique selling point of this instrument, which is the peculiarity of the instrument itself.
Yeah. Well, the seamless combination between temperature control and electrical control is certainly one point where we see many people interested in. Also, I would say the data analysis part. So how easy it is to get a curve, to perform a fit, to create and to see correlation between temperature, between current, between the different aspects. Because the main point here is that everything is integrated in the same instrument, in the same software. So it's very easy for the user to get the data, perform analysis, and go on with this type of characterization.
Right.
Which is in the end also selling point of BIOS, what we already do. Easy to perform all the measurement, or it's an all-in-one instrument in the end. And this is basically a replication of the same concept.
Great, thank you. Moritz, and another one for you. They're asking you if you did any degradation studies on your batteries.
Mm-hmm. Well, yes, we did. We cycled them for thousands of cycles at the moment. We're still a young startup, so we cannot do 10,000 of cycles yet. But we're working on it, and of course there is degradation, as with all all battery materials, but it's not that there's an abrupt degradation. So usually what we see over time is that the capacity goes a bit lower over time, but there's no abrupt failure, which you could maybe expect for lithium metal batteries, which we don't have.
They're also interested to understand if Dr. blades could be used for your batteries, or one has to use something like PVDs or some more complicated techniques.
So most commonly, PVD is used for thin film batteries. There are also other publications with other methods which are used. So yes, certainly there are different ways of fabricating it. But here we kind of also look at other industries, for example, the OLED industry. They're using vacuum coating techniques there since tens of years, and they also try to remove some of these vacuum coating layers since 10 of years, and they have not. We're not able to do so. So they're still using vacuum coating techniques there.
Yeah. I found that part very interesting because you were mentioning similarity. You are similar to OLEDs and PVs, and this is also why Fluxim is working on batteries as well, because we have an experience in OLEDs and PVs, and then battery was a natural choice for us. There is another one. How about the self-discharge rate with no load applied or the shelf?
Thanks for that question. So we have a very poor electrical conductor as a separator, and this allows us really to have a very long self-discharge range. So the cells which we're fabricating today, they're above or below 1% per month of self-discharge. But we know if we get the materials and the layers right, we are at about 1% per year self-discharge. And this from fundamental material properties, this is possible. Now it's basically you need to deposit the layers in a clean manner, and then you're at 1% per year. But we're already close to that. And this is again very different to what especially you have in capacitors, which did discharge very quickly, but also classic lithium-ion batteries discharge much faster than that.
Did you have any problems with the interlayer adhesion on the batteries?
Yes, that's another important question. Especially we work with materials which sometimes also have to be crystallized, and then also thicker layers that what is usually done with PVD methods, and then interface adhesion becomes sometimes an issue. But there are also tricks around that to avoid it. Sorry for not going into detail there.
Understand. There's one last question. How much energy density and power density could you expect from your battery at this scale?
So also we'll keep it quite vague, but from an energy density, we expect more than a classic lithium-ion battery today. And from a power density, more than about 10 times as much as what you expect from a lithium-ion battery today. So energy density, we can have some improvements, but this is not really where we are fully unique. Other solid-state batteries can also do that. We can deliver it in a very different form factor than others, and with the high power density.
Thanks. All right. Last one. Have you also considered the thermal stress across the layer stack?
Yes, definitely. That's also an important factor, especially if you go to these very high C rates. Right now, we have not looked at it from a simulation point of view. Let's say we will do this very soon to start this from the bottom up. Really build a proper model and simulate the thermal stresses in these cells. Right now, we don't see a strong issue of it. We don't see that the cells are heating up too much. Yeah, basically, cannot say a lot about it.
Okay, thanks a lot. I would like to thank you, Moritz. That was a great talk, and we really appreciate the collaboration that Fluxim is having with you and your company. Stefano, this was also a very interesting talk about this new technique, this new characterization tool we are developing. Our next webinar will be in 1 month, and we are going to keep in touch with you with the topic of this new webinar. And for now, I really wanted to thank you once more. Thank you, everyone. And we'll see you next time. Bye-bye.
Thank you very much. Bye.
Thank you. Bye.